Hello, everybody. I hope you are all doing well and you're ready to try another question. This is question number 12 on our Ontario Senior Math Contest from the year 1968. If you'd like to try the question, of course, I encourage you, as with the others, to pause the video and try it out for yourself. But what have we got for question 12? Develop a formula for the sum of n terms of the series. We just want n terms of them. And we've got 1 plus 2 times 4x plus 2 squared times 7x squared, 2 cubed, 10x cubed. And it looks like the general formula, each individual term is 2r, 3r plus 1, x to the r. Discuss under what conditions the limit of the sum of the n terms as n becomes infinite exists. So I want to know when does the whole thing sort of converge? What x values do I need? Okay, so first thing I notice, I've got this 2r here. I can sort of bring them together and call it 2x to the r. And I'm going to say something like let y equal to x. So our terms are now 3r plus 1, y to the r. Okay? So let's let Sn of y equal the sum of the first n terms, because that's what they want me to talk about. So that's going to be 1 plus 4y plus 7y squared plus 10y cubed. And it's so this has an exponent of 0, 1, 2. So we'll go up to 3 n minus 1 plus 1 y to the n minus 1. So that's the first n terms there. Okay. Now, I want a formula for this in terms of y, and then I can change it back to being in terms of x. The 2 I think is going to get in my way. What I want to focus on is the fact that we've got an arithmetic sequence here. Okay, we've got a sequence that starts with a particular value, you typically call it a, and it goes up by some constant amount each time. So the difference between 1 and 4 is 3, the difference between 4 and 7 is 3, 7 and 10 is 3. It just keeps going up by 3s. There's a nice little trick to working with a series like this. Let me show you what it is. Sn of y is 1 plus 4y plus 7y squared all the way up to, I guess we can say 3n minus 2 y to the n minus 1. I'm leaving a little bit of space here. And if you come along and you multiply by y, you'll get 1y, 4y squareds, 3n minus 5, y to the n minus 1s, and you'll get 3n minus 2, y to the n's. Now, I've lined this up for a reason, because what we're going to do is we're going to come along and we're going to subtract. We're going to be left with 1, and then 4y minus 1y is 3y's. 7 minus 4 is also 3. 10 minus 7 would be another 3. And you just keep going on like this, and you get 3s everywhere. That's the nice part of using the arithmetic sequence here. The fact that all the constants have a common difference. And this part in here will have a very nice expression, and then we also have subtract 3n minus 2y to the n. So Sny minus y, I'm going to write that as 1 minus y. Sny is 1 plus, now we can do 3y plus y squared plus y to the n minus 1 minus 3n minus 2y to the n. I'm going to group that first and last term together. And then we're going to say 3y minus y to the n over 1 minus y, just using sort of basic geometric series formula there. Okay, increase the power by 1 and divide by y minus, or 1 minus y. Okay. So there we go, and if I just want s and y, divide both sides by 1 minus y. So that'll be 1 minus 3n minus 2y to the n, all over 1 minus y. I don't think this can really be cleaned up. And then 3 y minus y to the n over 1 minus y squared. Okay. And then Sn of 2x and this is what they're asking for, sum of first n terms, would be 1 minus 2 to the n, 3n minus 2x to the n, 1 minus 2x, 2x minus 2 to the n, x to the n, over 1 minus 2x all squared. So there I've got a formula for some of the first n terms, and that is the first thing they asked me for. Some of the n terms of the sequence. Discuss under what conditions the limit exists. Well, for a fixed value of I think it might be easier to start with this expression. So for a fixed value of y minus, or 1 minus y and 1 minus y squared are fixed. But y to the n changes as n increases towards infinity. Okay. So what you want is, so either, depending on y, if y is 1, it sort of stays constant, and actually what you get, Sn of y is going to be 1 plus 4 plus 7 plus 10 plus, so this clearly doesn't converge. They do want me to talk about convergence, right? Under what conditions the limit actually exists. If y is sort of a similar story, it'll alternate 1, and then it'll go minus 3, and then it'll go plus 4, and then it'll go minus 6. This also doesn't converge. You could explain that a bit more in depth if you want. I don't think it's necessary. If y in absolute value is greater than 1, y to the n gets really, really, really big. So our expressions like what was it, 1 minus 3n minus 2yn, that's going to get way too big on the top there. Same thing with that yn over there. So again, the limit doesn't exist. The yns are getting too big, but if I pick y in absolute value being less than 1, then yn goes away after a while as n tends to infinity. Okay? So SNY's limit exists exactly when the absolute value of y is less than 1. Now, it's a power series. You could, of course, do something like ratio test or something like that to prove it. I'm not going to bother with that. I think this reasoning here is fine. But if you feel that this is incomplete or is going too quickly, of course, bust out root or ratio test. Either one are either one is fine, and would work perfectly for this sort of power series that we're making. But I think my work here stands for itself. So I need the absolute value of y needs to be less than 1. So Sn2x has a limit exactly when the absolute value of 2x is less than 1. So the absolute value of x needs to be less than a half. That'll make the sequence sort of converge. And what the heck, I don't think they ask us for it, but as n tends to infinity, the terms involving 2n and x to the n will just disappear. So we'll get y over 1 minus 2x, or sorry, 1 over 1 minus 2x. And then 3 2x over 1 minus 2x squared. That should be my expression in the end. Right? Yeah. That works nice. All right. They didn't ask for that, but it's nice to always be able to say, all right, if you have a value of x, this is what your sequence is going to look like. And there we go. That's question 12. We have just one more question to go. The last question, there it is, question number 13. It's a group theory question, I can see. It starts off with a multiplicative group, but I'm not going to read anymore. I'm going to save that for the next video. I hope to see you there.